Hey, Goose and Goose. I hope this is bright enough for you. But I'm doing QFT right now. I'm starting at the beginning of chapter 3. I know I haven't informed you about chapter 1 and chapter 2 yet, but we'll get there. And I'm basically just going through all the examples and making sure I got the fundamentals down, like actually doing out these things because that's how I'll actually know if I really know these things. So I'll show you what I've done really quick. So no fucking idea if you can see this. Is this gonna show up backwards? I have no idea. Okay. So, we're studying the Lorentz algebra, basically meaning we're studying the Lie algebra that the Lorentz group satisfies. Okay, so what we're going to do is we're going to be looking for the generators of the Lorentz group. If you remember, those are the elements of the Lie algebra. And they satisfy some commutation relations. And once you know the generators of the algebra, you can get back to elements of the Lorentz group by exponentiating. And so we're actually doing that. So first thing we're doing is we're going to look at what's called, I really hope this isn't backwards. If it is, I apologize. We're looking at the defining representation, okay? And we call it the defining representation because we get the commutation relation of the Lorentz algebra from this. Okay, so the defining, so the generators of the Lorentz group are these objects j, mu, nu, okay? Where mu and nu both run from 0, 1, 2, 3. Okay, so 4 because we're in special relativity. 4 vectors. So this is how we define it. So it's I times parentheses x mu del nu minus x nu del mu. And you'll notice that the indices switched because this thing is anti-symmetric. And you can actually show from the defining property of the Lorentz transformation is that if you act a Lorentz transformation on the metric g mu nu, you have to leave the metric invariant, meaning it's the same. And if you write that out, you'll show that the generators must be anti-symmetric. And so they kind of pulled this out of a hat, this equation. They got it because the rotations take this kind of form, x cross p, where, p is I dd ddx. There's h bars, but we set them all to 1 because screw that. So then they generalize it to 4 vectors and they get this thing. And what we're going to show is that when mu and nu, so obviously if mu and nu are equal, you get 0, because then if mu and nu are equal, you get 0, because then you have this thing minus itself, you get 0. So anti-symmetric, the indices can't be the same. So it turns out that when mu and nu are equal to spatial indices, meaning 1, 2, or 3, so time is 0 and 1, 2, and 3 are space. If mu and nu are space indices, like I and j, those correspond to to spatial rotations, like just rotating x, y, and z. And if mu is 0 and nu is I, meaning any 1, 2, or 3, those correspond to boosts, giving you Lorentz transformations which boost you. In the end, both of those are what I'll call Lorentz transformations. A Lorentz transformation consists of either rotations or boosts, or both of them. And this nasty thing right here is the commutation relations for the Lorentz algebra. It says that the commutator of j mu nu with j rho sigma is this long thing right here. And you can actually show by plugging in this with, use mu and nu and then use rho and sigma, and then multiplying all that thing out, and you will get this thing, where g mu nu is the metric, and we use the convention that it's 1 minus 1 minus 1 minus 1. And no matter what your representation is, meaning, no matter what, this is just one representation. This is an explicit form of a Lorentz transformation. Remember, a representation is a mapping from the abstract elements to a group of matrices. And you can have a representation of a group and a representation of an algebra. And so this is a representation, this commutation relation holds for all representations. No matter what representations we choose for the J mu news, they must satisfy this commutation relation. So the first thing we look at is called the vector representation, okay? And I remember telling you that what we do when we study QFT, one of the first things we do is we try to figure out how objects transform under Lorentz transformations, because that's the whole point of QFT is that it's quantum mechanics, but it's relativistic. And so we need to understand how these objects transform under Lorentz transformations. And different objects transform differently. Vectors transform under one representation of the Lorentz group. Spinors transform under another. Scalars transform under a different one. So they all use different mappings from the Lorentz group to a group of matrices in order to transform. So we're going to look at what's called the vector representation, which is the representation that 4 vectors transform under. So x mu, the position 4 vector, that will transform. You will use this Lorentz transformation to Lorentz transform. I know that sounds circular. Same thing with the momentum vector. The momentum 4 vector. You will use this representation to do Lorentz transformations. So they pull out of a hat. They literally say that if you let mu and nu label what matrix you're using, and alpha and beta tell you the matrix elements. Alpha will label the row and beta will label the column. So I know there's lots of indices running around. Alpha and beta will also run between 0, 1, 2, and 3, and mu and nu also run between 0, 1, 2, and 3. But you just have to remember that mu and nu tell you which matrix you're using, and alpha and beta tell you which elements of that matrix. And so the representation for the vector representation says that the alpha beta matrix element of the mu nu generator is equal to this thing: G mu alpha del nu beta minus G nu alpha del mu beta. And so if you want to figure out what the matrix elements are of J12 in the vector representation, you plug in 1 for mu and 2 for nu, and then again 2 for nu and 1 for mu, and you use the fact that G mu nu is 0 unless mu equals nu, and so it's diagonal, so it has to be 1 minus 1 minus 1 minus 1, and so like G1 mu is only non-zero if mu also equals 1, and then G11 is, remember that the first element is actually 0, so 1, 1 is actually the second diagonal element, and our metric goes 1, minus 1, minus 1, minus 1, so G11 is minus 1. And then, of course, like delta, the Kronecker delta 2 beta is only non-zero if beta equals 2. So delta 2 is 1 also. Delta 2 is 1, because Kronecker delta can only give you 1. I know, I wish I had like a camera up here that could look down on us so that I could be writing this at the same time. But I'm working with what I got, Goose. So anyways, this is the representation for that acts on vectors. And so to make sure that should be correct, what I wanted to do is I computed how a vector should transform under an infinitesimal Lorentz transformation. And if you remember how we did infinitesimal transformations, it was always 1 minus the parameter. Sorry, someone messaged me. Gabe asked if we still have the question for Physics Jeopardy. Oh God, no. Maybe Cameo does, but you'll have to wait for tomorrow. Let's see what he says. I missed Gabe. Okay, so remember it was 1, the infinitesimal transformation was 1, which is the identity, minus I alpha, where alpha is the infinitesimal amount that you're moving, times TA. And TA was the generator. But this time, our generator is J mu nu. There's just more of them. Turns out for the Lorentz-Lie algebra, there's 6 generators. And it makes sense because there's 3 rotations and there's 3 boosts. I can rotate along X, Y, and Z, and I can boost along X, Y, and Z. So six generators in total. So what I did is I said that V alpha, where V is a 4 vector, should transform to Kronecker delta alpha beta. So this is just the identity matrix, minus I over 2 omega mu nu J mu nu alpha beta V beta. Okay, so let's take a look at these two parts, this delta alpha beta V beta. That's just the identity matrix. So if you multiply this by this, you just get V alpha again. That's fine. That makes sense. Now this part, this is our minus I. Now alpha, instead of being just one number, is a collection of 6 numbers, okay? So this is omega mu nu, because you don't have to do just one of these at a time. Like I could do a rotation along the x-axis, a boost along the y-axis. You can do those all at the same time. And so this is basically saying that you're summing over all the different types of infinitesimal transformations. You know, you can boost and rotate all at the same time if you wanted. So omega mu nu is our infinitesimal either angle that you're rotating or boost. And J mu nu alpha beta is the alpha beta component, alpha beta matrix element of the mu nuth generator, where this is how the generator is defined. I know my finger's blocking it, so I'll let you take a good look at this, because you might not have had that. And I really hope this isn't backwards. Wow. And you can pause this at any time. Okay, and so what we did, we wanted to try it for, I wanted to do a concrete example, so I let omega 1, 2 equal theta, and omega is also antisymmetric, so that means that omega 1, 2 equals minus omega 2, 1. Switch the indices, you pick up a minus sign. So omega 1, 2 is theta, and omega 2, 1 is minus theta. And then I let all other matrix elements be 0. So basically, the only terms that are going to contribute to this guy are when mu is equal to 1, nu is equal to 2, and when mu is equal to 2 and nu is equal to 1. And you sum over both of those things because we're using Einstein notation. So, so what I did is I said I want to calculate omega mu nu, J mu nu, alpha beta for the 2 non-zero ones, which is 1, 2 and 2, 1. So it's let's see, it's omega 1, 2, J 1, 2 alpha beta plus omega 2, 1, J 2, 1 alpha beta. Okay, and then I just plugged in. So the first one is omega 1, 2 times J 1, 2 alpha beta. And now I went back up here to my definition of J mu nu alpha beta. And so I plugged in mu equals 1 and nu equals 2. And I used the definition of G mu nu and the definition of delta alpha beta in order to get this matrix. And I didn't write in all the zeros because I didn't feel like it. And then I did the same thing for, sorry, this should be omega 2, 1. Screw myself up. Now I did the same thing for 2, 1, omega 2, 1 times J 2, 1. And now I plugged in mu equals 2, nu equals 1, and again used the property, and I get this matrix. Okay, but now I needed to add them together. So notice these are the same matrix, so I just get 2 times this matrix. But the 2 will cancel out with this 1/2, which is just convention. And then delta, the delta, so that means that V alpha goes to delta alpha beta, which is just the identity matrix, which I've written there. And then minus the sum of these two matrices. They're both times I, so flip the sign on each one of these and get rid of the I, and then minus that. And you end up with this matrix. And this is the infinitesimal. Oops, I did not even write that correctly. This is an infinitesimal rotation around the z-axis. And this might look familiar. It kind of looks like cosine theta sine theta minus sine theta cosine theta, but you take theta really small, and cosine of theta small is 1, and sine theta of really small is theta. So that's the infinitesimal form, and it works. This is what a Lorentz transformation looks like. It's a 4x4 matrix which acts on a 4 vector. So we did good. Okay, and now the vector representation is not bad. Just you gotta actually chug through the computations. I'm gonna turn on the air. It's getting hot in here. Hi, Gus. Now, that was one of the representations, okay? That's the vector representation. Now, we want to figure out another representation. Because Dirac did this, and he was the shit. Okay, so Dirac said that if we can find a set of 4x4 matrices, gamma mu, where mu this time represents what matrix it is. There's 4x4 matrices, so there's gamma 0, gamma 1, gamma 2, and gamma 3, and each one of them is 4x4. So if we can find 4 matrices gamma mu satisfying the anti-commutator of gamma mu, gamma nu equals g mu nu multiplied by the 4x4 identity matrix. So we have gamma mu, gamma nu, and remember this just means that the indices are arbitrary, so mu could be equal to nu, mu could be not equal to nu, but this is what it equals, the anti-commutator. So this is gamma mu, gamma nu plus gamma nu, gamma mu, they switch orders, is equal to g mu nu times the 4x4 identity matrix. Because these are 4x4 matrices, so you have to get a 4x4 matrix on this side. Because this g mu nu is just a number. So Dirac said, if we can find 4x4 matrices satisfying this, then we immediately have another representation. We can immediately write down another representation of the Lorentz group. And I'll do that right now. Dirac said that if we define S mu, define S mu nu equal to I over 4, the commutator of gamma mu with gamma nu. So Dirac said that if we define S mu nu as this, notice this is the commutator, and this is the anti-commutator, because this defines gamma mu, gamma nu, and this is how we use them to define a new matrix, S mu nu. So once we have these, if we just set S mu nu equal to this S mu nu will satisfy this commutation relation, where this is now S mu nu, S rho sigma. And so if it satisfies that commutation relation, then it must be a representation of the Lorentz algebra, meaning it's a representation that satisfies the Lorentz-Lie algebra. And so if you plug in the definition of S mu nu into that long-ass thing, which I do not want to do, it's not instructive. I know I said I wanted to do all the examples, but that one's just, it doesn't do anything for me. It's just, can I not fuck up algebra? If you do that, then you have a representation of the Lorentz algebra. And let's see. So what he does is, he says, let's define, so we need to find those gamma matrices, those gamma mu nus, such that, sorry, lost my mind. If we find those gamma mu's that satisfy that anti-commutation relation, then we have a representation of the Lorentz algebra. So let's write down some gamma mu's. So he says that if we define gamma j equal to I, the complex number I, times sigma j. So gamma j equals I times sigma j, where this is one of the Pauli matrices, and j is either 1, 2, or 3, such that gamma I, gamma j equals minus 2 delta ij. Such that this holds, which actually, if you do the computation, is the same as this guy. Then we found the gamma mu's. Sorry, that only works for 3 dimensions. Wah. Let's find it for 4 dimensions. Because after all, we live in a relativistic universe. So, for 4 dimensions, we define gamma 0 to be 0, 1, 1, 0, and gamma I equals 0 sigma I minus sigma I 0. Okay. So gamma is a 4x4 matrix, and I know this only looks like a 2x2 matrix, but each one of these elements is actually another 2x2 matrix. So this is the 2x2 matrix of zeros, and this is the 2x2 identity matrix. So gamma 0 has off-diagonal identity matrices, and gamma I has off-diagonal Pauli matrices, where this one's minus. And if we define these, they will satisfy this relationship, and thus we can generate S mu nus. And that specific representation of the gamma matrices, because you could find other gamma matrices which satisfy the same thing, but this certain representation is called the Weyl or the chiral representation. And I believe most high energy theorists use the chiral representation, this representation. And so then we can immediately define the S mu nus. So we can write S0I, which is I over 4 commutator of gamma 0 with gamma I. And evaluating that, you get minus I over 2 sigma I 0 0 minus sigma I. So that is S0I, and if you remember, the 0I is a boost. So this thing will generate boosts. Will generate boosts in the x, y, and z direction. Then Sij, which is I over 4 commutator of gamma I with gamma j, is equal to 1/2 epsilon ijk sigma k 0 0. And that is Sij. And this guy will give you rotations. It's pretty cool. And now, remember that these are 4x4 matrices. They just have 2x2 matrices as their matrix elements. It's fucking crazy. So these 4x4 matrices, S mu nu, act on objects with 4 components. And you think to yourself, okay, what has 4 components? Isn't that a 4 vector? Didn't we just do the vector representation? You'd be wrong. These objects are called spinors. Spinors are like vectors, except not. One huge difference is if you rotate a vector by 360 degrees about any axis, you get itself back. If you rotate a spinor by 360 degrees, you get itself back times -1. Spinors have 4 pi periodicity. You need to go around twice to get back to the same place. Probably some crazy topology and differential geometry stuff that I don't understand. And then once we have these, we have the generators. We can exponentiate and get an element of the Lorentz group. We can get a Lorentz transformation. One thing that's interesting is that if you remember Wigner from the lecture that we watched with the Asian lady, Wigner always says that we want our representations of groups in physics to be unitary. Unitary, again, means, I'll give you 5 seconds. Okay, unitary means U times U dagger equals the identity matrix, where dagger is the transconjugate, the complex conjugate and transpose. And it turns out that if you want to write a unitary matrix as the exponential of another matrix, that other matrix must be Hermitian. And I'll show you that right now. So let's let U equal e to the a, and we'll have U dagger equal to parentheses e to the a, close parentheses, dagger, just like that. And you can, let's see, give me a second. This should just be ETA. Wait, shouldn't it be anti-Hermitian? Did I fuck up? Guess I fucked up. I don't remember why. I just know that if you want a unitary matrix, which is the exponential of another matrix, that other matrix has to be Hermitian. I'll figure it out though. Wow. Okay, but anyways, what it turns out is that our boost generators, S0I, are not Hermitian. And so therefore, when we exponentiate, we won't get unitary group elements. And so something's fucked up. The reason is that the Lorentz group, it turns out, is not compact. And compact means the same thing it did in topology. Either every open cover has a finite subcover, or the sequential version, which is every sequence has a convergent subsequence. So every sequence has a subsequence that converges to something. And the Lorentz group is not compact. And it turns out that when you study Lie algebras and Lie groups, that if you have a non-compact group, there are no unitary finite dimensional representations. So this is a finite dimensional representation because, you know, this is a 4x4 matrix. So that's a 4x4 representation, which is finite. But it's not unitary. It won't give us a unitary matrix. It turns out that you need infinite dimensional matrices in order to get unitary transformation, unitary group elements for a non-compact group. So if your group is non-compact and you try to make a finite dimensional representation, it won't be unitary. But you can use an infinite dimensional representation and make it unitary. We haven't covered that, and I don't actually think that this book covers infinite dimensional Lie groups. I think Hermann Weyl himself discovered the infinite dimensional representations. I don't know anything about that, though. Okay. So, let's look at some things. August. I gotta go to the gym. It's 8:10. I told Riley I would go. But I will do more of this, Goose, and I'll make another YouTube video, and I'll keep doing this, and it's like you're right here with me, Goose. Okay? Wah, 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 wah. Love you. Bye, Goose.